Okay, everybody, welcome back to System Software. Let's get started. So last time we looked at functions in Simple C last time, their semantics. Does anybody have any questions about Simple C functions before we start? Okay. Does anybody have questions about functions in general? So I got some questions at office hours about like how, at least at the hardware level, functions are implemented with the stack and all that, and with return addresses, return values. Any questions on that? Does anybody want to see that again, or something in more detail? Yeah. Okay. All right. Let's do that since I think we're gonna have time for this. All right. Let's just do it here.
Quick question.
Yeah.
So our main function looks something like def main and something like that, right? So in the LLVM function, how is it going to look like? Is it going to look like def square?
Dev square?
So what I mean is like you already give us the main.
Yeah, so I'll talk about this today. So I made a slight change to Simple C functions to avoid having to do global variables. So it'll be a little simpler to implement. But I'll go over that. You won't put a main method. So I gave you a template without the main method. But you'll see.
Yeah, because I was confused, like what would our function be called in LLVM?
Yeah. We'll go over that. Today, after this, we'll talk about code generation for functions. But I want to go into a little more detail about how how functions work in like a real world machine, like an Intel architecture, and how it works with the stack in order to implement recursion or any kind of function calls. So the main concept is what the stack allows you to do is it allows you to freeze the state of a function so that you can kind of pause the state, go off and do some other work, and restore the state. The reason this is possible is because our machines are deterministic. If you give it the same input, it's going to give you the same output. Without any randomness, you give it the same input, you get the same output. What that also means is that at any point during the execution of the machine, if you save all of the state of the machine, which is the registers and the memory, if you save all that, you could even just write it down on a piece of paper. A year or 10 years later, if you restore that state to your machine, that machine will execute as if nothing ever happened. The machine won't know. Make sense? Do you believe this? Does anybody not believe this? Okay. So yeah, basically the machine's deterministic. So whatever is the state of its memory and its registers at any point in the program, you're going to have the same outcome in that machine. And so the way functions are implemented takes advantage of this fact. So even if we've got a recursive function like factorial, so let's just make this simple. If x is less than or equal to 0, let's return 1. Otherwise, we return x times fact. The classic factorial function, right? So let's see what happens when we run this program for factorial of 3. So recall that the stack is just a location in RAM. Your random access memory just has one word for each slot in memory. You can address one word of memory at a time. So it's basically like a giant array of data. And typically when we draw these diagrams, we have address 0 at the bottom and the maximum address at the top, whatever that happens to be. And the way, at least for Intel architectures and common architectures, the stack begins at the top and grows downward, or at least Yeah, so it's kind of confusing because the bottom of the stack is at the top of the memory address. So this is the top of the memory address. This is the top of the stack, and the stack grows downwards in memory. The heap, whenever you use malloc, the heap grows in positive memory addresses. But anyway, today we're talking about how the stack works. Questions on that? Questions on kind of the memory layout? I think probably you should have learned this in computer architecture if you took it. Okay, so the way, the behavior that we want for functions is that when we make the function call, it doesn't affect any of the state in our currently executing function. So if we've got a main method, and inside of main, say I create a new variable x, assign it to 3, and a variable y, and I want y to be the result of factorial 3. And maybe I want to print x plus y. So I don't want any of the state of main to be changed or affected when I call factorial. But inside of, at the processor level, there's no notion of functions. So if main is using the same registers as factorial, they're going to step on each other's toes. So what we really want is all of the state of main to be held frozen somewhere while we go off and execute factorial. So the way this works is we use the stack to record all of the state about this function. So when main was called, we put into the stack all of its local state. So y equals something. So say y gets initialized to 0 in this case. C doesn't really do that. So we have all of the information that we need about main so that if we happen to stop executing main and wanted to pause main and go do something else in our machine, as long as we restore all the state of the machine, all of its registers, all of its memory, then we can just continue executing main as if nothing had actually happened. Okay, so let me show you this in practice, what this looks like. So let me number these lines here. And we'll see why this is necessary in a second. Okay, so this is the stack frame for main. And the stack frame is just all of the state about that function that we need in order to return to it or in order to go back to the caller of that function. When we enter main, we assign x to 3, and then so in C you can actually declare y and assign its value in the same statement. But what really happens is fact3 gets called first. So whenever a function is called, the caller, in this case main, constructs a stack frame for factorial, and that stack frame will contain the parameters, any local variables, space for the return value, and space for the return address. So all this information is pushed onto the stack, and it's done by the main method. Whoever calls factorial pushes that information onto the stack. And so that stack holds the parameters, local variables. It actually might end up holding any registers that need to be saved, but we won't worry about that. It holds a space for the return value. So even though we don't know the return value yet, the caller allocates some space for it so that when we return from this function, we can recover that return value. And also the return address. So this is how, even though, so once we get to the end of the function here, the end of fact, we need to know who called us, at what program point we were called so that we can return to it. And because there may be many functions that call factorial, in this case we actually have 2 functions that call factorial. Factorial calls itself. There may be different return addresses. So the way we solve this in the stack frame is to store the address of the next instruction after the function call. So this would look a little bit more detailed if we were looking at assembly, but for all intents and purposes, the return address for the call of factorial in main, we can think of the return address as being line 9, as being the next instruction that gets called. This is actually not strictly true, because the next thing that it has to do is update the value of y. But just to make this a little simpler, so we're not looking at assembly, just think of it as the next. Does everybody know about the program counter in the processor? Nobody learned about this? Who learned about the program counter? Who didn't learn about it? Okay. So the program counter is just the current the address of the current instruction that you're running in the machine. It's just a special register, so that you have this fetch and decode. I don't know. It's an architectural thing. So it automatically runs the instruction, updates the program counter, runs the next instruction, and if you have a branch, it just changes the program counter to whatever you're branching to. So the return address is really just the program counter at the point of the call plus 1. So the next instruction after the call. That's where we want to return, because that makes sense, right? After we're finished with the call, we want to go back to the callee, or the caller, the function that called our return function. Okay, so we can think of the return address as 9 here. It's a little bit of a hand-wavy thing, but let's use that. Okay, so when we call function 3, we start. I wish I had a laser pointer on here. Oh, I do, here. Okay, so when we call factorial of 3, the function call branches us to the beginning of the factorial function here. So we go along and we execute all the instructions of factorial, but before we end this function, there's another function call. This function call is to factorial of x minus 1. We know that the current value of x in this instance of factorial is 3. So we get a function call of factorial with parameter 2. With me so far? Any questions on this so far? So the caller, in this case, the caller is fact itself, creates a new stack frame to hold all the state for this new function call that we've made. All the while, we have the previous function call, factorial of 3, its state is frozen on the stack. It's still there so that we can come back to it and continue processing this function. But so once to process this call, we create a new stack frame for the function call factorial of 2. And so it does the same thing as before. It creates space for the parameter, space for the locals, there are no locals here, space for the return value, and space for the return address. So in this case, the return address is, so what is approximately the return address for this call to the function, more or less? So is it 9? No, it's not 9, right? It's going to be something inside of factorial. So strictly speaking, it would be, the next instruction would be the multiplication if we were looking at the assembly for this. But for all intents and purposes, let's just say that the return address is going to be line 5, somewhere in line 5. If we looked at the assembly, there'd be a specific multiplication. That would be the next instruction. So notice here that even though we're calling the exact same code, we're branching to the exact same code, the state of that function is different. It has a different return address, has a different return value. So this, you can almost think of this as like a different instance of the factorial function, kind of a different variation of the factorial function. Okay, so we've constructed this new stack frame for the call to factorial with parameter 2. And so the call just brings us back to line 2 to start executing this function again. And once we get to this another call to factorial, because x is still not less than or equal to 0, we get another call to factorial. But this time the parameter is 1, factorial of 1. So just like before, we get a new stack frame set up by the caller, who creates space for the return value, for the locals and the parameters, and also the return address. So what would the return address approximately be for this call to factorial? 5, yeah, it would be 5 again. All right, so we've got Okay, so then we execute everything for factorial of 1. We get yet another call to factorial, but this time the parameter is 0. 1 minus 1 is 0. And that gives us a new stack frame where the parameter is 0. We have some return space for return value and some return address, which is, again, 5. Now this time, when we go to execute factorial, we see that x is indeed less than or equal to 0. So now we get a return statement. So what the return statement does is it actually populates the return value in the stack frame. So actually on Intel, you can return things via a register. It's much more optimal, but to make this kind of simpler, let's just see that the return value is in the stack frame. So there's definitely an optimization here where you can just use the registers to return it. But anyway, conceptually speaking, the return value is communicated to its caller somehow, either through memory or through a register. And then once that return value is, once factorial of 0 is finished, how does it know what to do after the return instruction? So it can't just keep executing. That would be definitely incorrect. So it needs some way to return to the point at which the function was called. So how does it know where to go after the return of the function? Yeah, the return address. The return address tells us exactly where to go. So for f of 0, the return address was on line 5. I mean, more precisely, it's just after the function call. And okay, so after the function call, the calling function now knows that factorial of 0 has a return value of 1. So it can substitute it in this multiplication and construct its own return value. So its own return value is going to be, so the caller destroys the stack frame. So now we're back in f of 1. And it constructs its return value using whatever the return value of fact 0 was, which is 1, times its value of x, which is also 1. So its return value is 1. Questions on this? Yeah.
Is the way that the stack is implemented, where you have the return address as the last thing, is that significant, or is that just the way it's happening?
I don't know if this is actually the real ABI. So if you look at like the Intel calling conventions for, I can never actually remember this, but I think I linked to it. Before. There's actually a nice, so I think, really, so it's here. So you can see the return address is here. It's actually before the local variables. So you have the parameters, the return address. You actually have a pointer to the previous stack frame, which I didn't really go into. I was just sort of hand waving that. This is actually a pointer to the previous stack frame. So it knows, where in the stack the caller's stack frame was, and then the local variables are here. And notice there's actually no return value here, because return value in this scheme, in the Intel x86 System 5 ABI, it's returned through a register. But the salient point is that there's some convention about where the return value is stored so that the caller can recover it. And in fact, parameters are actually passed through registers as well in this calling convention. But these are kind of hardware specifics, and they're also system dependent. So to make it simple, I'm just going to put everything on the stack and kind of hand wave some of the details. Okay, so we're back here, but because our current stack frame is the stack frame corresponding to the call of f with parameter 1, we know that x is 1, and we were able to construct our return value. So at this point, now we hit the return. Now we return again, and when we return, we use the return address to tell us where to go, and substitute in the return value for the call in the caller. So f of 2 called f of 1. f of 2 needs the return value of f of 1, but now we've computed it. We've finished executing f of 1. So now we know what the return value is. So f of 2 can substitute that value here in its multiplication of x times factorial x minus 1. And so that allows, that tells us that the return value for fact of 2 is 2 times 1. So its return value is 2. Yeah.
Well, in the F3, the function 3, why is the written address 9? I think I feel like it's returning to 8.
We'll see. That's a good point. We'll see when we go here. That's true. Yeah, that's probably right. I'll change it to 8. And I'll explain why when I get there. Because I was hand waving, I didn't show you the assembly, so it's a hand wavy a little bit when you look at source code. Okay, so we've finished executing f of 2. We have its return value. So now we need to return to the place that called it, which was the function f of 3. That's what called f of 2. So once we return to f of 3, it tells us our return address is 5. So again, we return here. But and the caller f of 3 destroys. Whoops, I forgot to destroy the stack frame for f of 1. So the caller f of 3 destroys the stack frame, recovers the return value, and uses it to compute its return value. So looking at the stack frame, we're in the stack frame where x equals 3, and it just computed f of 2, just asked factorial to compute f of 2, which gave us 2 for the value of f of 2. And so now f of 3 can complete its computation, and its return value is going to be what? What is its return value going to be? 6. Good, yeah, 6. It's going to be whatever its value of x was times whatever the value of fact x minus 1 was. In this case, x was 3, so it's going to be 3 times fact of 3 minus 1. It called out to factorial to compute f of 2, so now it knows that f of 2 is 2. So its return value is going to be 3 times 2, which is 6. Questions? All good? More or less. Okay. So now we're just about to finish executing f of 3. But in this case, its return value is not 5 anymore. Its return value is inside of main. So I put 9 before, but to be like pedantic, we could have said it was on 8 because the next instruction is going to be an assignment to y. But the salient point is that the stack frame records the place to return to, the return address. And in this case, the last thing that called factorial was main at this point. So its return address is no longer going to be 5. It's going to be some point inside of main. And so we know the return address, or we know the return value. We use the return address to bring us back to line 8 inside of main. So now main can destroy this stack frame and recover its return value. So inside of main, it can actually substitute for factorial. It can substitute 6 here. So then it can assign y to 6, and then print x plus y, which is what in this case? 9. Yeah, good. So it can actually substitute this in. 3, 6. So it'll print out 9. Questions on this? You with me, or is this like too confusing? Did I say it in a convoluted way? Pretty sensible. Any questions? Questions on this? What are your questions? So actually, if you work through this and you ever have a challenge, ever a recursive algorithm is giving you a challenge, you can realize how it's actually implemented under the hood. If it's compiled language, it's actually implemented like this under the hood, and you can trace it. You can actually trace out the program by knowing the concrete input for a recursive function. And even if it's like tree traversal, or there's many recursive calls, multiple recursive calls, not just kind of a linear recursion like this, it works the exact same way. And this is actually the reason why you can do tree traversals with a stack or with recursion. Because if you have a compiled language, it actually is going to be a stack under the hood. Yeah.
How does the machine know how much space to allocate? So does it like just keep allocating space as the call keeps like?
Yeah.
If you're in an infinite loop, that it would just keep allocating.
Have you ever seen Stack Overflow? Have you ever heard of Stack Overflows?
Yeah.
Like Stack Overflow website? Stack Overflow is a recursion that has unbounded or requires more space than the memory you have allocated for the stack. So if you're like writing your tree traversal algorithm and you forgot your base case, it's basically going to be like an infinite while loop filling up the stack.
It will just keep going down.
It'll just keep going down the stack until you run into the heap or you run out of allocated memory for it. So I think usually there's a bound on the stack size. Yeah. So even though you have virtual memory, you have like a huge address space, the system will bound how much stack space a program is allowed to have, I think. Questions on this? Questions? Okay. So fortunately, you're using LLVM, so you don't actually have to worry about managing the stack. LLVM will do this all for you. That's why I didn't go into too much, intricate detail about how this works. If we were implementing this for like the Intel architecture, yeah, we'd have to go into a lot more detail about how the stack actually works and follow this calling convention. So it wouldn't all, not everything would be on the stack. You'd actually have to follow this convention. Although, yeah, if you wanted to be able to link with other programs, you could always make up your own convention for your own program, but it won't be able to link with other libraries. Okay, other questions on the on functions, on project 4, or anything? Other questions? Okay, so I made a little bit of a change to the grammar for project 4 to make it easier to implement. The one downside is that it won't be backwards compatible with the rest of the projects, but I think that's okay. No?
What does that mean that it will be?
Okay, I'll show you what it means. So I removed global variables altogether because if you do global variables, you're going to have to use a different syntax in LLVM to do it. You wouldn't just be able to put them inside of main, local to main. Because if you have a variable that's local to main in LLVM, it won't be global. It won't be accessible to your other functions.
So if you call a function inside your LLVM main sending some variable, it won't work unless it's global in LLVM?
No, you can pass parameters, but yeah, you wouldn't be able to have global variable without doing this extra syntax. So I figured it would just be actually easier for you guys to just have no global variables. So you can certainly do it as a bonus project, but no global variables, and all the variables are just function local. So I'll show examples of what this looks like. This makes the kind of variable management easier because the global table is only for functions and the local table is only for variables. So no kind of complicated lookups into parent scopes. By all means do this. I'll give you bonus points if you want to try this. You have to look up the syntax for LLVM global variables. It's really not that bad. You can totally just do that. But yeah, so I think this should make things easier. I hope. Should make it easier. So the backwards compatibility is kind of annoying, but it's not that bad. It's only a little bit not backwards compatible. So I updated the grammar. Oh yeah, another thing is I'm enforcing that the return statement has to be at the end of a function. So that means I won't give you a test case where the return function is somewhere inside of the function because it actually makes it a little more complicated in LLVM. You can't just arbitrarily throw a return statement in to LLVM and then have a branch after it. Return statements have to be the only thing at the end, before a label at the end of a block. So the return statement will always be at the end of a program. Trust me, that'll make it easier to generate the LLVM IR. Okay, so the change to the grammar is actually really minor. The only change is right here. It just redefines what a program is. So before, a program was declarations, functions, statements. And those statements were part of the declarations were like a global variables. But the way I've had you implement it all semester is that those declarations were part of main. So instead, the top level program is just going to be a list of function definitions. That's actually the only change to the grammar. Yeah, that's really the only change. But it kind of changes the semantics a little bit, has consequences to semantics. And it has consequences for backwards compatibility, because now you can't just have declarations and statements at the top level of the program. They have to be wrapped inside of a function. That's the backwards compatibility. So if you want backwards compatibility, you could have a little flag in your program that just switches between allowing declarations at the top level or not allowing it. It's a very minor change. The rest of your parser generator or your grammar or code generator should be identical. Really should be identical, more or less. And also, so then what this means is that you have to create your own main method. So whereas before our template had main built in to it, there was you wrapped all of your statements and declarations inside of a main function in LLVM. Now, because we have function definitions, you don't need that anymore. You don't need a template that has main in it. You can just write a main function in simple C, and your compiler will turn that into an LLVM main method. Make sense? So I thought about this at the beginning of the semester. I didn't think of a good way to make this like backwards compatible. There probably is a way, but it involves making like LLVM local global variables, and yeah, that was disappointing. I mean, maybe, we've been doing them as local all semester, so you'd have to it would still be like not backwards compatible.
So now our program has to work like the first thing in the simple C will be in main, right?
Actually, it probably should be the last thing.
Yeah, probably. Yeah, that was it.
So the functions should be defined before they're used, kind of like in C. Yeah, as long as the functions aren't calling each other. So you won't be able to do that in simple C because we don't have function declarations. We just have function definitions. But anyway, minor thing. We can.
So our simple C program cannot call it like the function cannot do the factorial.
No, it can call itself. So by the time you hit the function definition, it should be inserted into the global table. But it's just that if after the function, you define some other function that you want to call, you won't have encountered it yet to add it to your symbol table. So the way C resolves this is, if you've probably noticed this, where you try to define these functions, like, oh, this function is not defined, or you get a warning. So what do? You put a little declaration at the top of the function, and then it just works. So we don't have to do that. We could do that. If you want to do that, by all means. It's actually really not that hard. You just rip out this part of the function and add it as a declaration. So that's the only difference, is that there is an extra kind of declaration where you can declare functions. So I often mix up, declaration and definition, but this actually has an important difference. Declaration is just saying what the type of a symbol is. It doesn't provide any code of any kind, actually. It just tells the compiler, this symbol is of this type. A definition has all of the code inside of a function. It's like the difference between a declaration and an assignment. The assignment actually means there's going to be some code behind it, whereas the declaration just tells the compiler, hey, here's a symbol, here's its type. So you could certainly add function declarations to the language, and then you can do what you do in C. But you don't have to do it. I wanted to make I want to make this very, very simple to implement. All those extra bells and whistles just cost compiler writing time. Okay, questions so far? Yeah.
And the other bonus project that we have for array, how's that gonna be like? Are we gonna call malloc in our simple C?
I think the version I have there, they're all fixed length arrays, constant length arrays. So you wouldn't have to do malloc. You can allocate that on the stack.
And you're just gonna create the space for LLVM.
Yeah, LLVM has instructions for doing this. It's kind of like a array declaration. So LLVM has language reference for this. If you're interested, I can point you in the right direction. Yeah.
So then we're not going to really use the template you gave us anymore?
Oh yeah. So it actually is almost identical. So what I did is maybe a little hacky, but I gave you a new macro inside of the template. So if you go to template.h, there's a new macro called Project 4 Prologue, aptly named, and it's identical, except I just removed the beginning of main. I just removed, you just don't need this. You don't need this anymore. You don't need the main because you now have functions in Simple C. So you can just write main in Simple C. Yeah.
Is the epilogue still the same though?
You don't actually, well, no, you don't need an epilogue anymore. Because look at the epilogue. The epilogue is just the return and the end of curly brace. But your function compiler will generate that. Will generate that for you. So yeah, this is a little hacky, but yeah. So I say this in the project 4 description. I say, here's the new template. Here's some examples of. We'll go over this today. The examples of actually translating Simple C stuff into programs. It's actually not that. It's really not that hard, but it is a little tedious. There's sort of a lot to keep track of when generating these functions. Way easier than dealing with the stack and with like the Intel calling conventions. But there's still a little bit of trickiness to generating functions. And that's what we're going to go over today. So other questions on this? Other questions on these changes? So they are kind of minor changes, but they do have an impact on backwards compatibility, and they do kind of have an impact on the semantics. So there's no more global variables anymore. Well, another way to think of it as everything you've been doing before has just been the contents of a single function, a single hard-coded function. And so now you're going to allow the programmer to make their own function instead of having to use a single hard-coded function. Questions? Questions on this? Okay. I'll take that yawn as a no. All right, so let's look at, do I have anything here? Yeah, okay. So let's look at, this is a function in Simple C. Looks, identical to C at this point. And you know what this looks like. You have the type of it, the name, the type and name of each parameter, comma delimited. And yeah, you have some computation inside and a return value. So in C is very pretty loose. You can put a return statement anywhere. You can leave out a return statement, and actually it might compile if you don't have strict checking on. But for us, the return statement always has to be the last statement. That'll make the code generation way easier, especially for LLVM. Okay, so function definitions in LLVM really kind of look a lot like C function definition. So this is what an LLVM definition looks like. It should look kind of familiar if you were looking at the template. You use this define keyword. You give the return type, just like in C. You give the name, and instead of a % sign, it's an ampersand. Ampersand means global names in LLVM. And then you give it a parameterized list of the types of the parameters. So unlike C, you don't have names for the parameters. We'll see how we actually get the values of them. But otherwise, it looks, really just looks kind of like C. And then you've got your curly braces delimiting the beginning and end of the function. Questions on that? Yeah.
You know how in C, you can pass by value or pass by reference?
Yeah.
Can you do that in LLVM? When you pass in the address and actually
Yeah.
in your main, things will change?
Yeah. So I'm gonna just say that main should just be take no parameters. Although you certainly could accept, the argc and argv. Argc and argv are part of the C standard runtime. So when you compile your LLVM output for your compiler, it will use the C runtime, and you could actually use those values to get the command line parameters. The problem is Simple C doesn't have pointers yet, unless you want to add them. So there's no way in Simple C to express what a pointer is. Maybe you could convert it to an integer and then do something like that, but you would need a way to express what a pointer is in Simple C. Now in LLVM, the pointer is expressed similarly to C using a star. So you can see LLVM has a huge amount of inspiration from C. In fact, it was originally designed for C compilation, if I'm not mistaken. But yeah, if you want to say there's a pointer value, then you just say just like before. So this is a signed integer of 8 bits, but a pointer to a signed integer of 8 bits, if you want to do that. But you don't need this. You don't need this for this project. But by all means, add pointers to simple C and do that. That would be cool. And in fact, if you do arrays, you will effectively have something like a pointer. You'll have the beginnings of pointers. Okay, so that's function definitions in LLVM. Pretty straightforward. So function parameters are a little bit different. LLVM sets up these special registers as the parameters to the function. So in our definition, there were no names. There's no named parameters. Instead, LLVM just sets the first, however many parameters you have, the first 0, 1, 2, 3, 4, whatever registers are going to hold your parameter values. And so effectively, the parameters are stored in registers for you. And so what you need to do in order to use these parameters completely is to allocate space for them on the stack. So why am I saying that you should do this? Why should you allocate space on the stack for the parameters if you've already got some LLVM registers that hold their values? Does that make sense? Yeah. In case there's another function call? Well, so LLVM handles all the stack stuff for us. So if there's a 0 inside of main and a 0 inside of factorial, there's not going to be any. They're not going to step on each other's toes. But yeah, good guess. So couldn't we just, like, wherever we see a parameter, like in mults, couldn't we just replace this with money %(0), %(1)? I mean, could we do that? Would that work?
So
yeah,
when you pass an int left and int right from
yeah,
the name, you're passing in some variable, right? Like %T1 or
well, the values of they're going to end up being %0 and %1 in your function.
So whatever you're passing, they're just going to turn into %0 and %1.
Right, the values will be in there. So you could say, like, add %0 to %1 and store it into T1. You could do that, and that would actually work in this case. But is there any potential problem with that? Like, let's say I assign left to be right times 2. In LLVM, I can't reassign registers. So the parameters are basically, at least in C semantics and in simple C semantics, the parameters are just other local variables that you can modify and update as you want. So that's why I'm saying you should allocate space for them on the stack. There are certainly cases where you wouldn't need to, like you could optimize this so that you don't have to do a stack allocation, but LLVM will do that optimization for you. So I'm recommending that you just always create stack allocations, just like you do for local variables, for your parameters coming in. So that means if you know you have 2 parameters, you just create a stack allocation just like you did for local variables, and then instead of storing nothing, which was what we do for local variables, store the value of the parameters into that address. With me on this? Questions on this? So I've taken the recommendation of using the name of the variable, which is it's a good idea. You can also do that. Unless somebody named it T1 or something. And then, so maybe don't do that. Okay, so that's how we set up the function parameters. The nice thing about this is that we can just treat parameters as if they're local variables. So we add them to our local symbol table, just the same way we add local variables. And in fact, if somebody has tried to define a local variable of the same name as the parameter, that should be a type error, just like it is in C. It's a type error. So this is the exact same code from the last slide, but now this is what your scope's going to look like. Your symbol table is going to look like once you set up your parameters. Questions on this? Yeah.
So then we're not going to deal with pointers and whatnot, right?
No, not unless you want to. Yeah, we won't deal with pointers. Okay. So there's several steps to generating these functions. It's really just about like kind of bookkeeping the symbol table. That's mostly what's going on here. So we need to, for the equivalent simple C function that we have, like multiply takes an integer and takes two integers and returns an integer. We need to emit the equivalent LLVM function definition, the function prototype that has its return type and name. We need to collect all the parameters, as we're parsing, we collect all the parameters in their types and emit the parameters for the LLVM function. So it's really just like a kind of straightforward source-to-source transformation where, you read in a simple C function and just generate the equivalent LLVM function syntax. Then we need to create the local scope, update our current scope, so we're no longer inside of the global scope. We don't want to stay inside the global scope. We want to enter our local scope. Emit the stack allocations for our parameters, storing the values, so that, %0, %1. And then, we're done setting up the function, and we can just dispatch the rest of the code generation to our declaration and statement functions, which, you've already written if you've implemented Project 3. And finally, when we're done with that, we just restore the current scope back to, not pointer, why does that say pointer? Back to parent scope. So if you're not doing nested scopes, there's only going to be two. There's going to be the global, which always has functions, and the local, which you construct for each function that you compile. But declaration, yeah. So you could probably optimize this. You can feel free to implement this how you like, but this is one way to do it. All right. Any questions on this sort of conceptually what we need to do? All right, so here's some pseudocode. It is fairly long, so let's just go through it. Let's go through it carefully. So in black, we have the parsing, what the parsing does. So let's kind of ignore the red for a second, if you can do that. The red actually stands out more. But so if we just remember how we parse the function, let me show you the grammar again to kind of refresh your memory on the grammar. So the grammar was, read the type name. For the basic simple C, it's just int. Read an identifier, read an L_paren, and then this complicated combination of regular expressions and is really just saying 0 or more parameters. So if there's one parameter, it'll match int and identifier, and then this will be 0 because it's star. If there's 0 parameters, then that question mark means this entire group doesn't have to exist. And if it's 2 or more, the first parameter will be read through these tokens, and then 0 or more combinations of comma followed by int followed by identifier. So it's really just the regular expression way of having a comma delimited list where there's no comma at the end of the list. Questions on that? Questions on that syntax? Okay, so that's getting the parameters, and then of course we have the curly brace to start the body, and then 0 more declarations followed by 0 more statements followed by the end curly brace. And notice this is exactly what was in the top level program non-terminal for Project 3 and earlier. Questions on this? Okay. So let's look at the pseudocode for processing this. So let's just look at the black text first. The black text just shows the parsing of that grammar. So we consume the int keyword, we get the identifier, which is the function name, we get the parentheses, and then the way I have this written is I check to see whether the next token is an identifier. If it is, I consume that identifier, read in the identifier, and then while the next thing is not a closed paren, while not done, then we keep reading comma and another identifier, comma, identifier, comma, identifier, until the next token is no longer a comma. So, not done here. I'm being a little hand wavy, but you basically do this while loop until the next token is no longer a comma. Yeah. Yeah, you can think of it like that as well. Although, yeah, that should be fine. Okay, so then the next thing you do is you consume the right paren, which is closing off the parameters, and then we read in the open curly brace, read in 0 or more declarations, read in 0 or more statements, and then the close brace. So that's it. That's the syntax. The production for functions is translated into recursive descent parser. Questions on that? All right, now let's dig into the code generation. So you can see that we're pretty much like, for each piece of the simple C, we're generating a little piece, the corresponding piece of LLVM, because LLVM is like quite similar to C and simple C. So it's actually it's almost like a one-to-one mapping from simple C to LLVM. So when we see an integer, when we see our int keyword, we just emit our define I32. That's the equivalent in LLVM. So if you were doing the typed version of simple C, where you have multiple types, you'd have to change this a little bit to keep track of different possible types and emit different types. When we get the function name identifier, we emit the function name with the @ sign, which is how we talk about global symbols in LLVM. And actually, one thing I forgot here is you have to update the global symbol table as well. That was in the last slides. You have to update the global symbol table as well. Let me add that very quickly. So okay, a little hand wavy, but so you also have to, you should add that to the current scope. Okay, and to handle the parameters, we want to do two things. We want to emit the equivalent LLVM parameters, which is just the LLVM types. We want to emit I32 for each of the parameters. But we also want to keep track of the names of the parameters, their names and their types, if you're doing the typed version. And so in my, because this is pseudocode, I can write this however I want. I just initialize a list of parameters, and whenever I consume an identifier for the parameter, I just add it to my parameters list. So now I've got this nice list that tells me what all the parameters are for my function. And if you're doing the typed version of this, you're going to have to keep track of both the parameter and the type. And after I collect the names of the parameters, I emit its type, I32. And for the comma, whenever there are commas, if I see a comma followed by an identifier, I just use a comma followed by the LLVM type. Okay, so that's how I process the parameters for LLVM. Any questions on this? Okay. Oh man, this is very buggy. Sorry. This actually is also supposed to consume the type name as well. Okay. All right, so, I did have the current scope. Sorry about that. Got ahead of myself. All right, so once we've read the function and the parameters, we can now construct the local scope for this function. So the first thing we do is we take what our current scope is, which, for most of you will just be global, and add our function to the global scope. And now we are free to construct our new scope. So to do that, we create our new table, we save the old scope. This is more relevant if you're doing nested scopes, and update our current scope to be the local scope we created for our function. With me on this? I think I talked about this last time. So it's pretty much the same as last time. Okay, so now I need to create those stack allocations for my parameters. And to do that, I have my, since I have my list of parameters, I can just loop over each parameter and emit the allocation and store to that stack address for each one. So we know that, by LLVM's definition, the parameters are going to be in registers named %(0), %(1), %(2), et cetera. So I just increment a variable I and construct the name of that register. So %, whatever I is going to be the register that holds that parameter, starting from 0. So let me just walk through this. So for each I from 0 to the length of parameters minus 1, so that gives me, if there's 10 parameters, I'm going to iterate over this 10 times. I get the name of each parameter, generate a new register for it to hold its memory address. I update that mapping in the symbol table between the name of the parameter and the location, the memory address for the parameter. I emit the stack allocation. And then finally, I store the value of the parameter into the stack allocation for the parameter. So I know this is riveting stuff. Questions on this? Questions? It'll be much more gratifying when you implement it and see it work. And so that's it. That's pretty much it. That's pretty much all we have to do. And then, because we've already written declarations, those will just work. They'll just work as they're supposed to, as they worked before on Project 3 and earlier. And same with statement. And finally, we just consume this end curly brace and emit the equivalent in LLVM, which is also a curly brace. And finally, restore the scope to whatever the parent was. So for the simple version of Simple C, that will just be the global scope. Questions on this? All good? Okay.
It seems easy, but I feel like there has to be some trick that's going to happen.
No, it's easy. It is easy. It is easy. It actually isn't that hard. It's just implementing, lists and stuff, and C is going to be, that's probably going to be the challenging part. Okay, so return is just another kind of statement. If you see a return, if we look at our grammar for this, it's just another kind of statement. So just like print, you evaluate the expression first, put it in a temporary register, just like we do with, read or print and assign. And whatever that register happens to be, so in this case T3, we just generate this code. That's it. It's almost like one-to-one for correspondence to see. Questions on that? Questions on return value? Okay, so that's function definitions. We still have to worry about function calls. So function calls is actually even more straightforward because we're using LLVM. It looks almost like C, so it makes it pretty simple. So remember, we're just storing all functions in the global symbol table, so this makes lookup really easy. If you see the syntax for a function call, how do you know you have a function call? Well, if you look at the syntax, it's in here inside of factor. This is our syntax for a function call. If you see an identifier and that identifier is followed by an open paren, then you know it must be a function call. So you can tell the difference syntactically between variables and function calls. If it's a function call, generate the code for a function call. And this, the syntax or the kind of regular expression I use for this is very similar to the parameters. This means 0 or more expressions, comma delimited. That's all that is. Function calls in LLVM, which you've already kind of seen for print integer and read integer. You set some new register equal to the call keyword, and then you have to actually give the type of the function, so the return type of the function, the name of the function, the @ symbol means it's a global value, and then the actual parameters. These are going to be the results of calling the expression code generator on each of the parameters. So you can see how since you've already written the expression code generator, this just plugs right in to your existing code generator. You just call this expression, save the temp value, and use that as your parameter. Yeah?
So in that example of the call, that were the T3 and the T4 like an X and a Y?
In here?
Yeah.
It's just an example. I mean, yeah, I think I took it from this. Oh, you mean an X and a Y? Where's?
Yeah, it's like would to T3 and T4 just to be the values of say int X and int Y?
In the caller. I'll show an example of it. So So recall the difference between the formals and the actual parameters. This is the function call. So like in my factorial example, this is the definition, and this is the call. So T3 might be the number 3, for instance, in the call. That's the call of the function. But yeah, good question. So this is equivalent to using the function in C, like in our factorial function or here. Whereas the define is equivalent to, I mean, the syntax even looks very similar, is equivalent to our function prototype. And so in, the formal PL world or compiler world, these are the formal parameters, the things that get substituted, just like in algebra. And these are the actual parameters. And so notice for the formal parameters, they're not named in LLVM. They're just %0, %1. And the actual parameters are just whatever register or value. If you can put a constant there in LLVM as well. They're just whatever register or value you happen to evaluate the expression to be. So going back to our grammar again, notice that each of the actual parameters is the syntax of an expression. That's why you can say like f of x minus 1. X minus 1 is an expression. But you've already written if you've done project 3 and project 2, you've already written the expression code generator. And your expression code generator you just call it, it generates code and gives you back what the temporary register is. And all you have to do is plug that in here to the actual parameter of the call. Questions? Questions on this? Okay, so here's the pseudocode for generating the call, the function call. It is probably also going to be kind of deceptively simple again, because it just looks exactly like the simple C function call. When we see the function name, so you'll have to do a little work to distinguish between variables and function names. I've simplified this a little bit. But we consume the function name, make a new register for the return value of that function call. Emit this call syntax. You just emit this exact call syntax, plugging in the variable stuff. So we emit the new register that we created, emit the syntax for doing the call, and you need to make sure you match the LLVM syntax. I was trying to save space, but you need the type for the call. And then if you see an open paren, you just emit an open paren. It's the same. It's like almost the same syntax. And then you can just do some kind of clever syntactic checking to say, okay, if the next thing is a right paren, then we have no parameters. There's nothing left to do. Otherwise, we need to start parsing all of the actual parameters of this function call. So according to our syntax, after the open paren, there's going to be an expression. Expression, you just call it. It will do, as long as it's implemented correctly, it will do all the code generation for you and return the temporary register. So you just emit that register name. That's just emitting this here. Make sure you have syntactic LLVM. This is just pseudocode. But yeah, you just emit that parameter that you got from generating the code for expression. And this just handles, a sequence of commas and expressions. But it's exactly the same thing. Until you no longer see commas, you keep parsing and generating code for expressions and keep emitting that register as parameters to your function call. And then finally, we get rid of or finish out our parameter list with our close paren. Questions on this? So this is like effectively source-to-source transformation, basically, where the syntax is very similar, and there's all sorts of uses for doing source-to-source transformation. Like you can do refactorings, and there's all sorts of clever things you can do with this kind of approach. And if you're really interested in this, there are more principled ways to do this, where you have a syntax tree first, and then you just do it. I mean, this is effectively a tree traversal, but you can do a syntax tree traversal and do pretty printing or even some simple static analyses. If you're interested in that, let me know. I can point you in the right direction for that stuff. Questions on this? Questions on function calls? Pretty easy? Does it sound easy? Or just boring? Or both?
I'll get back to you on that.
Okay. All right. So, okay. So, yeah. So as I mentioned before, the input program should have a main for it to be executable. So I'm not going to give you any programs that mess with this. I'm going to give you programs that have mains. I'm going to give you programs that have returns at the end. All of the stuff I say in the notes on semantics in the grammar, I won't trick you with that stuff. So you can just assume this, and it's left as bonus exercise to actually verify this. So is there anybody programming Java? Who's programming Java? Did you ever get the error like not all paths have a return?
Yeah.
You got that, right? So that's like C doesn't do that, but you can actually write an analysis that checks. Oh, do all the paths have a return statement to it? So you could actually write that in this case. You can actually check that. So that's something you can do, with this kind of technology. You can do those kind of more fancy analyses on code. Of course, some code may not be reachable because it's dead code. But okay, so let me actually show some examples of these simple C programs and equivalent LLVM code. Whoop. Where was I? Okay, so I have this. This is actually, there are links to this in the end of the project 4 description. Actually, I can just show it here. It's probably a little easier to read. So I've got a nice long simple C program here. Actually, let me get some syntax highlighting. Oops. Okay, so I've implemented a couple of functions here. I've got a main. I have 2 implementations of factorial, or recursive implementation, and an iterative implementation that uses this multiply function, which is super useful because our language already has multiplication. But I just want to show more functions. And we have the equivalent LLVM code for this. So this is just the template that is now in project 4 prologue. It's just the same template without the main method. So let me get down to the actual recursive function. All right. So I implemented this by hand, so it won't, it'll be close to what your code should look like. But you can see here that int factorial recursive was transformed into define I32 recursive, and the parameters were transformed into I32. And then we've got the stack allocation for our parameters. So this is for the parameter x. You can see I allocate the stack and then store the value of register 0 into the stack. Questions on this? Any questions on this? Yeah.
So when you said %x, it's supposed to be %t1 or something.
Yeah. However you generate new registers, just use that. Yeah, and then this is just, all of this is just the result of calling declarations and statements. This entire body of code here is just declarations and statements.
Imagine the rage if intro and CS1 had to be written in LLVM.
Imagine if what?
The rage of students who.
Oh yeah, if you had to write in LLVM.
CS1 had to use that.
Well, maybe you'd like C better if you probably like C a lot more if you had to program in LLVM or assembly. So that's just the body of that's just the body of this function, and you can see that we've got the recursive call here. So LLVM handles all of the function calls for you, so the recursion will just work, and you can see the equivalent. So notice that this single statement in C is just you know this from implementing the assignment, but it's broken up into these sequence of statements. We've got the We're loading x into T3, that corresponds to this. We're loading x again into T4, that corresponds to this x. You could certainly optimize this. We'll talk about this next week. Then we're doing subtraction of x minus 1, and that becomes, this T5 is x minus 1, that becomes the parameter to our function call. So this section here is calling expression on the parameter to factorial recursive. Expression just gives us a temporary variable, so we use that in our function call to factorial recursive. Once that returns, so this is what I was trying to get at when we talked about the stacks. That's just one step in our larger x times factorial recursive expression. So that's one factor in the expression, just like negation or looking up a variable was one factor in our expression. So once we have it, we have the value in T6, we can continue on to do the root of this expression, which is a multiplication. And finally, this is an assignment to result, so that's the store for updating the result. Questions on that? That's hopefully mostly review. And then the return value is just computing whatever the expression to the right of the return keyword is, which in this case is loading from memory, and then just generating RET, the return. So it's almost like one for one, C to LLVM. Of course, that's by design, actually. Questions on this? So I've given a couple examples. So this is an example where you've got multiple parameters. So I have to allocate one stack slot for each of these parameters. %0, %1. And I think that's pretty much it. So you can look at this example. You can use this for testing your code generation. Here's more function calls. Questions on this? Questions on any of the function stuff? Yeah.
So I imagine this is obvious, but if we're given a function that hasn't been declared, it's just the usual error statement, right?
Yeah. That's a good point. Yeah, I need to define those actually. So you could actually probably use the same error message. Maybe I'll just do that to make it simple.
Yeah. Well, you just have like a test case with it.
I'll make a test. Yeah. I'll make a test case for it. Funny autocorrect. Questions on functions? Everyone's good on project 3?
Working.
Okay. I think that, when is that? When's that due?
Yeah.
14th?
Next Thursday.
Okay, so we got another week for that, and then project 4 will start. And so we're actually getting rapidly approaching the end of the semester.
Yeah.
Don't be too excited. No, that is exciting. So then so next time we're actually going to start talking the more advanced topics. That doesn't have to be implemented, but we're actually going to talk about optimization. Some of these more obvious things, like when you have the same register or the same variable being used over and over, you can optimize that. And then, we'll go on from there. So anyway, let's stop it there. We only have a minute left. So everyone have a good, is today Thursday? Everyone have a good weekend, right? Everyone have a good weekend. Have a good long weekend. Yeah.